An exponential equation is an equation where the unknown appears in the base or in the exponent. We have seen these exponential equations already in the previous chapter about powers and power functions, but now that we have learned about logarithms, we are able to solve the more complex types of these equations. Let us first revise that there are two types of exponential equations. Type 1, the unknown is in the base. So x, the unknown, x to the power of q equals c. For example, x to the power of 3 equals 8. And we get as the solution x equals 8 to the power of 1/3, or the third root of 2, so of 8, so 2. In type 2, the unknown is in the exponent, so we have some base to the power of x equals some constant c. So for example, 2 to the power of x is 16, and we find x is 4, because 2 to the power of 4 is 16. And we have solved that by saying, well, 2 to the power of x is equal to 2 to the power of 4. So from there it follows that x equals 4. So how to solve exponential equations? X to the power of q equals c. This means x is equal to c to the power of 1 divided by q, or this is the q's power of c. Well, how did we do that? What we do here is we take both sides to the power of 1 divided by q, and x to the power of q, the whole thing to the power of 1 divided by q means I have x to the power of q times 1 divided by q, so x to the power of 1. What is important is to remember that if the q is a integer number, eine ganze Zahl, and it is even, that we have two solutions, namely the plus and the minus solution. So let us look at this example. X to the power of minus 6 is 729. So we get plus minus 729 to the power of minus 1 divided by 6. Using here the 1 divided by q, or 1 divided by minus 6 would be the exponent. Well, we get rid of the minus in the exponent by putting everything into the denominator. So we have plus minus 1 divided by 729 to the power of 1/6, which means plus minus 1 divided by the 6th root of 729. And well, the 6th root of 729 is 3. So we get final result plus minus 1/3. For the type 2 equation, b to the power of x equals c, well, we know by definition this is that x equals the logarithm of c in base b. If we have a logarithmic equation, then that means that the unknown x appears in a logarithmic expression. And the solution idea, what we try to get is that the logarithm of x in base b equals some logarithm of a number in the same base b, and then we know that x is equal to this constant c. Okay, let's solve example 1. Well, when we have 2 to the power of x equals 20, we want to get x, so what we have to do is we have to take the logarithm in base 2. So we get logarithm of 2 to the power of x in base 2 equals logarithm of 20 in base 2. And now using the logarithmic identity 1, this says that the left-hand side is just x. So we get x is logarithm of 20 in base 2. We could have got that also directly using the definition of the logarithm. Here, by definition of the logarithm, x is logarithm of 20 in base 2. However, it's also a very simple way to not to have to think about this definition of the logarithm, just use the logarithmic identity. So always take the logarithm in the same base as we have it here. So and then we know, okay, this is just x. Now apply this idea to solve example 2. Stop the film. And here comes the solution. Well, we take the logarithm to base e, which is logarithm naturalis. So we get ln of e to the power of x equals ln of pi. And again, using this logarithmic identity 1, we have ln of e to the power of something is log in base e of e to the power of something, so it's just the x. So x is ln of pi. Look at example 3. Try to solve it on your own, and here comes the solution. Well, we do again take the ln, so we get ln of the whole expression equals 2. And now we have just what remains. Ln of e to the power of something is just the exponent, so 3x plus 1 is 2. Here, logarithmic identity 1, minus 1, 3x equals 1, divide by 3, and we get final result, x equals 1/3. Try to solve example 4. Here comes the solution. We take the logarithm in base 2. We get logarithm in base 2 of 2 of the whole expression. Oops. That equals to logarithm of 7 in base 2. We use the logarithmic identity 1. We have 2x divided by x plus 3 equals logarithm of 7 in base 2. Now just remember, this logarithm of 7 in base 2 is just some strange number. It'll be a little bit less than 3, so it could be maybe 2.8. And now we have to solve it. Just imagine for a moment it would be just 3. What will we do then? Well, we have to multiply with x plus 3. So we get 2x is equal logarithm of 7 in base 2 times x plus 3. Next thing, we expand. So we get 2x equals logarithm of 7 in base 2 times x. Maybe we could make here the brackets just to make it very clear that it's only logarithm of 7. And now, remembering again, this is just a number, so we have to get all the x's on one side. If this was just 3x, what would we do? Well, minus 3x, so we do just minus this number, log of 7 in base 2 times x. We have to subtract that, so we get 2 minus log of 7 in base 2, the whole thing, so many x's we have, equals 3 times log of 7 in base 2. And the last thing is we divide by this number here, so the number of x's we have here. So we divide by 2 minus log 7 in base 2. And we get that x is 3 times log of 7 in base 2 divided by 2 minus log of 7 in base 2. When trying to solve example 5, we have a problem here because we have a plus, so we might say let's take logarithm in base 3, but when we have logarithm of u plus v, so logarithm of this whole expression, we can't do anything with that. You remember, we only have if logarithm of u times v splits into logarithm u plus logarithm v, but logarithm of u plus v is nothing. So that doesn't help. So instead, what we'll try is, can we make one expression using that? Well, the idea is very simple. You can try on your own, and otherwise here it comes. Well, we can split that as 3 to the power of 5x times 3 squared plus 3 to the power of 5x equals 90. Next step, 3 squared, that's just 9. So we have actually 9 times 3 to the power of x plus 5x plus 3 to the power of 5x equals 90. And well, 9 plus 1. We have 9 times this expression plus 1 this expression. So we have in total 10 times the 3 to the times 3 to the power of 5x. Just imagine if this was 9z plus z, obviously you have 10z. And this z is just a complicated expression, but you have 10 of them now. So that equals to 90. And now we divide by 10. We have 3 to the power of 5x equals 9. Now, well, you can try on your own. Here comes the solution. We take the logarithm in base 3. So we get logarithm of 3 to the power of 5x in base 3 equals logarithm of 9 in base 3. Or maybe let us just rewrite immediately the 9 as 3 squared. And we know both sides we have logarithm in base 3, so this here has to be the same like that one. So we have 3 to the power of 5x equals, oh no, sorry, now I make it unnecessarily complicated, my mistake, sorry. What I wanted to say makes more sense is actually to say, obviously, here using the logarithmic identity, I get 5x, and on the right hand side I get 2. So I'm just losing this logarithmic identity 1, and divided by 5 I get x equals 2/5. Now have a look at example 6. You can try to solve that on your own. I'll show you 2 possible solutions. There are many different ones. Okay, here comes the first one. We write that as 3 times 3 to the power of x, because 3 to the power of x plus 1 is 3 to the power of x times 3 to the power of 1. So that equals 5 times 2 to the power of x. Now let's divide by 2x and by 3. So we get 3 to the power of x divided by 2 to the power of x equals 5 divided by 3. Now we can rewrite that left hand side just as 1 power, namely 3/2 to the power of x equals 5/3. And now we'll take just the logarithm in base 3/2. So we get logarithm in base 3/2 of 3/2 to the power of x equals logarithm of 5/3 in the base 3/2. And using the logarithmic identity as always, we have x equals logarithm of 5/3 in base 3/2. Another way of solving this, as I said, is, let me just quickly rewrite it here. Okay, let's say we'll take directly the logarithm in base, whatever we like, let's say in base 3. So we get logarithm of 3 to the power of x plus 1 in base 3 equals logarithm of 5 in base 3, so 5 times 2 to the power of x in base 3. Well, the left hand side is just x plus 1, and the right hand side is logarithm of 5 in base 3 plus the logarithm of 2 to the power of x using the laws of logarithms. Laws of logarithms, which the 1, L1, plus, and then let's use immediately the L2, because logarithm in base 3 of 2 to the power of x is just x times the logarithm of 2 in base 3. Now, remembering this is now again just a number, so I have a certain number of x, so I have to subtract that to put all the x on one side. So I'll take minus x times log 2 in base 3, and I'll subtract also the 3 here on the left hand side. So what I get is x minus logarithm of 2 in base 3, the whole thing times x, equals to logarithm of 5 in base 3 minus 3. So factoring out the x, I have 1 minus logarithm of 2 in base 3 times x equals logarithm of 5 in base 3 minus 3, and I get x equals logarithm of 5 in base 3 minus 3 divided by 1 minus logarithm of 2 in base 3. Well, now when we look at these two results, it seems at first sight they are completely different, and it's not obviously at all that they are the same. However, if we want, we can show that. I will not do it now. If you like, you can somehow try to change this expression, try to change this one, and in the end it'll turn out it's the same number. You can obviously just use your calculator to find out in decimal writing just how much is this value and how much is this one, and hopefully I'm really right. And luckily I've just checked it, not with the calculator, but otherwise, and I've realized I made mistakes here. Obviously, this is just x plus 1, and so we have to subtract here 1. So all this here is a 1, and then really we get the same result. For those interested very quickly how to see that this expression is really this one, well, 1 is just logarithm of 3 in base 3. Since I'm subtracting it from logarithm of 5 in base 3, I get logarithm of 5/3 in base 3. So I have the 5/3 here. This is the logarithm of 3 in base 3 again. I'm taking now logarithm of 3 in base 3 minus logarithm of 2 in base 3, so I can write it as logarithm of 3/2 in base 3. So up here I had logarithm of 5/3 in base 3, here logarithm of 3/2 in base 3, and using now the change of base rule sort of backwards, I get exactly logarithm of 5/3 in base 3/2. Example 7 is difficult. Let's do it together. So we keep the left-hand side unchanged and we rewrite the right-hand side without a negative exponent. So e to the power of minus x is just 15 divided by e to the power of x. Now let's get rid of the x in the denominator. So we multiply with e to the power of x. So what we get is e to the power of x squared minus 2e to the power of x equals 15. And here now the idea is we make a replacement. We replace the e to the power of x by a z, and we subtract 15. So what we get on the left hand side, z squared minus 2z. This is the replacement, the e to the power of x by z, and then subtracting 15, I have minus 15 equals 0. Well, here that you should be able to solve using the factorization. We see it's z, once plus and z minus. The product has to be 15, the difference 2, so it's 5 and 3, and it, to be minus 2 in the end, we have to have z plus 3 and z minus 5. So we get the z1 is 5, z2 is minus 3. And now we replace back using the z equals e to the power of x. So we have e to the power of x equals 5. So what we have to do to find x, we take ln, and we get x is ln of 5. Here we get e to the power of x equals minus 3. Well, a power expression can never be negative, so there is no solution here. We have got only one solution here. A small reminder, useful for some exercises maybe. B to the power of 2x is the same like b to the power of x squared. So if we have an equation where b to the power of 2x occurs and b to the power of x, then we have actually this situation here, and we should use the substitution b to the power of x is z. In example 8, let us look at the logarithmic equation. You can try to solve it by your own. Here comes a first hint. The problem is that we have here a logarithm minus a logarithm. We have everywhere the same base 5. This is fine. However, what we need is one logarithm in base 5 equals another logarithm in base 5, not a difference of two logarithms. think about how you could rewrite that as 1 and then how to solve it. And here comes the solution. Well, we use the laws of logarithm 2. We can rewrite the right hand side then as logarithm in base 5 of 8 divided by 6 minus x. And now this means that x equals 8 divided by 6 minus x, because only then the logarithms are also the same ones. So let's multiply with 6 minus x, and then let's do that once. So multiply with 6 minus x, so we get 6x minus x squared equals 8. And now to have we have obviously a quadratic equation. Let's add x squared and subtract 6x, just because I like to have the x squared positive, and I put everything on the left hand side. So I get x squared minus 6x plus 8 equals 0. Using factorization, we get x minus 4 times x minus 2 equals 0. And so we find x1 is 4, x2 is 2. These are the two solutions of this equation. The next two examples are about inequalities. Here you see both times a larger. So find all n, natural n, such that 2 to the power of n is larger than 10. The idea is we solve, instead of the inequality, the equality, and then we just say, well, what does it mean? When does this expression become larger? What happens when n becomes larger? Well, the whole expression becomes larger, and from there we can follow what is then the correct result. Let's do it. So we do 2n to the power of n equals 10 using, well, the logarithm in base 2. We get n equals logarithm of 10 in base 2, and that's approximately 3.3. So 2 to the power of 3.3 is equal to 10. Now, if I increase the n, the 2 to the power of n will become also larger. This means I'm looking for an n that is larger than the 3.3. So I'm looking for the solution are all natural n. So all n larger or equal to 4. Now try to solve example 10. Do it on your own, and here comes the solution. Set the expression equal. Then we take the logarithm in base 1/2. So we get n is equal to the logarithm of 1 divided by 100 to the base 1/2, which is approximately 6.6. And now what happens when, so we know 1/2 to the power of 6.6 is equal to 100. Now when n becomes larger, the larger n becomes, the smaller the whole expression becomes, because I multiply more often with 1/2. However, I want this expression to be larger than the 100, so the n has to be smaller than the 6.6, which means n has to be smaller or equal to 6. The next two examples are very or even extremely difficult. They are only for those interested. You can try to solve them on your own, or otherwise just after each step try if you can continue on your own. So let's start with example 11. Here comes the solution. The idea is we take the logarithm in base 3 on both sides. In the next step we apply the law of logarithm 3. So we get this expression here on the left hand side, namely we just take the exponent in front of the expression logarithm of x in base 3, and this is just logarithm of x squared in base 3. On the right hand side I just changed the n to 3 to the power of 2. Next step, I use again the law of logarithm 3 for this expression here, and I get this result here. Just this simplifies to 2 times logarithm of x in base 3. Well, the next step is just to rewrite that as 2 times logarithm of x in base 3 squared. Just looking at it here, I have once this expression here once, so this whole squared, so that equals to 2. I divide by 2 both sides. I have logarithm of x in base 3 squared is 1. We take the root. We get logarithm of x in base 3 is plus or minus 1. And now the next step, I do 3 to the power of the whole both sides. So I get 3 to the power of logarithm of x in base 3 equals 3 to the power of plus minus 1. And using here the logarithmic identity 2, I see this is just x. So x is 3 to the power of plus minus 1, which means x1 is 3 and x2 is 3 to the power of minus 1, which is just 1/3. Have a look at example 12, and here comes the result. We take logarithm in base 5 on both sides. Well, what I get here is logarithm in base 5 of this whole expression. I can take that using the logarithmic, the law of logarithms 3. I get that in front then. So I get logarithm of x in base 5 times logarithm of x in base 5. So what I get is just logarithm of x in base 5 squared. Here, when I take logarithm in base 5 of this expression, I can use split that using the logarithm, the law number 2 of logarithms. So I get logarithm of x to the power of 3 in base 5. Well, logarithm of x to the power of 3 in base 5 is the same, like 3 times the logarithm of x in base 5 minus the logarithm of 25 in base 5. Now let's do a replacement. We replace the logarithm of x in base 5 by z. So we have actually z squared equals 3 times or 3z, and the logarithm of 25 is 5 squared, so the logarithm here is just 2. Now minus 3z plus 2. We have now the quadratic equation, 3z squared minus 3z plus 2 equals 0. Using factorization, we get z minus 1 and times z minus 2 equals 0. So the first solution is z1 equals 2. Second solution, z2 equals 1. Replacing that backwards, we get logarithm of x in base 5 is 2, and logarithm of x in base 5 is 1. And now using 5 to the power on both sides, we get 5 to the power of log x in base 5. That is the law of identity 2. We get just x equals 5 to the power of 2, so 25. And here we get x to the power of x equals 5 to the power of 1, so equals just 5. As I said, these last two examples, 11 and 12, are for those interested. If they were too difficult for you to understand, no problem. Focus rather on the rest.